In this video, we're going to learn about temperature. Now, temperature is defined as the average kinetic energy in a sample of particles, and kinetic energy is the energy that objects have in motion. So kinetic energy is defined as 1/2 mv squared, where m is the mass of the object and v is the velocity of the object. So how heavy something is and how fast it's going will influence how much kinetic energy it has. In a sample of gas particles, there will be some particles that have a higher kinetic energy, some with a lower, but their average will be related to their temperature. Now, let's look at a simulation here. What we have is I'm going to take a bunch of particles and put them into this chamber. And here they are moving around. Now, I can see that at 300 degrees Kelvin, they have an average speed of, it's around 420 or so meters per second, maybe a little more. And I can see there's this distribution. And note, there's an average, but some particles have lower speed and some have higher speed. And if I were to take this sample, though, and I were to raise the temperature from 300 Kelvin, let's go up here. Let's go to, say, here we go, keep going. Say from 300, I've gone a little above 900. Notice how the average speed has increased now. We're at around 800 meters per second. Notice also that the distribution of particle speeds is a little bit broader, but the average is shifted a bit further to the right. We have a higher average speed. And that's how temperature will affect the speed of gas particles. And note that kinetic energy also has, on average, increased from a rather narrow distribution that was smaller. We have a little bit broader of a distribution and a bit higher of an average now that we've raised the temperature. But next, we're going to see what happens when we have multiple different gases, multiple different types of gas. And that we will get here. All right. So if I insert, let's see, we're going to put in the same amount of lighter gas particles, and they have the same temperature. Notice how these smaller gas particles at the same temperature are moving at a much higher speed. That's because in the case of these samples having the same temperature, we need to have 1/2 mv squared be equal for the big particles and for the small particles. So what we know is that since they have the same kinetic energy, the small particles need to be moving faster in order for their mass times their velocity squared to be equal to the mass of the heavier particles times their velocity squared. And that's what we're seeing. If you notice here, what I've done is, I've got in white all of the sort of the average of all the particle speeds, but you'll see that the red particles, there are fewer of them at a lower speed, more of them at a higher speed. This is a broader distribution with a higher average. In the case of the bigger blue particles, their average speed is lower and they have a narrower distribution. This is dynamic and it's a little bit hard to see at times, but we can see that exact same reality probably a little bit more cleanly displayed in this graph right here. Oxygen is very heavy. Hydrogen is very light. Hydrogen H2 is 2 grams per mole versus oxygen's 32 grams per mole. And you'll see that hydrogen has a much broader distribution and a much higher average velocity than oxygen does at the same temperature and kinetic energy. So that explains temperature. Hope this video has been helpful. Please feel free to leave any questions or comments in the comments section below. Thanks for watching.